So this is the beginning of an interval, this is the end of the interval, and we have a function, I'll call f of x, dx, and that function may look like this. Here's B, and there's area between the curve and the x-axis, and this tells you compute area. Okay? And we have computed that area in a couple of different ways. One way is we use geometry and we figure out rectangles and triangles and circles, correct? And just kind of add them up, okay? The other way is we use left Riemann sum, right Riemann sum, midpoint Riemann sum, and trapezoids to approximate, correct? Right. And the idea behind this is then eventually we came to the definition of an area that says, all right, if we have an infinite number of rectangles, that's what that means, n is rectangles, and we compute the area of those rectangles. And so that means we're going to add up all those areas, and we have some type of counter. We can use I, we can use K, and we add them all up. Well, we need a width and a height. The width is going to be B minus A over
Trying
N.
to see, it's hard to see. Could someone
They're
please
better?
close the blinds?
Blinds are closed. You know what? I'm going to turn off the lights and see if that's better.
I don't know why is this hard to see for once.
No. Is that better?
Much better, thank you.
Okay. Where two things are being added. This right here, which is the width that we call delta x. And then we put in a function, a value. That value starts at A, and we're going to add this delta x. That is really messy. I'm going to rewrite it over here. The limit as n goes to infinity. I'm adding up k equals 1 to n, b minus a over n, times, and down here I'll write it f, starting at a, and we're moving over b minus a over n times k. All right. So what we're going to be doing in the next 2 weeks is transitioning from this approximation way to come up with something called the antiderivative and how it applies to computing area. That's where we're headed. This thing had a name. It was called the definite integral.
What's the definite integral? Which one?
This thing right here. And so if you notice, it's written right here. It says, last lesson we learned about the definite integral, which is this, represents the area under the curve on the interval from A to B. Did that help at all? Moving on?
I think you need to refocus it.
Okay, let's try this. That help? Not really?
I don't know what's with it today.
Well, I kind of know, but. It looks like there's got to be a bad spot or something. All right. Okay, so let us say that the interval starts at A, but we do not know where it stops. That gives us an interval that looks like this. We're going to start at A, some number, and we're going to keep going. We're going to keep that interval open.
A to x.
Yep. Where A is a constant and x is some unknown variable. We can represent this function so it looks like this. It's gonna start at A. X is gonna change. And we're gonna need a different variable in here, which we're gonna call T. This X is changing and this is different, okay? This is giving us our heights. So I'm gonna give you an example. We're gonna call this capital F. And we're gonna call this an accumulating function. What I have here is I have a graph. This right here is F. And we're gonna complete this table. So we're gonna start at 0, and we're gonna move to 0. So if I'm there, exactly how much area do I have right here? Do we have any area? None. So what we do is we say we have 0 area. Now I'm going to move to 1. So right here is going to be my area. I'm going to shade it in. And Owen, how much area would you say that is?
2.5.
That's what I would say too also. So now we're going to move to 2, and we're going to have some more area.
Oh, so F, capital F represents the area.
Correct.
I thought that was the graphics. I thought that was the line itself.
No, this right here is F. Capital F is the area. Exactly correct. So Ben, how much do I have now?
I said 1.5.
Pardon?
1.5.
Well, I gained 1.5, but I have more area, correct? I have to add all of this because I'm going from 0 to 2.
I see. So it'd be 4.
4, perfect. And then I'm going to go to 3, and I gained more area. And so, Colin, how much would that be now? 5, perfect. And Grace, I'm moving to 4. 5.5. Okay, Austin, you got the tricky one. Down to 5. Why is that tricky?
Is that negative?
Yeah.
0.5?
Yeah? So what am I at now?
Oh, 5.
I'm back to 5. Okay? I turned around here, didn't I? Right? I went the opposite direction. How far did I go opposite? That amount. Is that making sense to everybody? All right, so like I said, this is called an accumulation function. And capital F accumulates area as X increases. Or you can lose some area, right? Because Austin said, hey, we lost a half, didn't we? Okay? All right, so that's part 1. Okay? We're going to learn something called the fundamental theorem of calculus. And you'll see me write it as FTC. And we're going to start, there's 2 parts to the fundamental theorem of calculus, and we're going to learn the second part. So this is going to be part 2. You haven't learned the first part yet. And so in math, we have things called add, subtract. Audrey, how are add and subtract related? Right, we call them inverse operations. There's another one, multiply, and its inverse operation is divide. They kind of cancel each other out, don't they, Owen? If I multiply by 2 and then immediately turn around and divide by 2, nothing happened, correct? If I add 15 and lose 15, nothing happened, correct? So when you see this symbol and this symbol, dy dx and this integral are inverse operations. So, if you're taking a derivative of an integral, what happens here is the equation does not change. This lowercase f stays as it is. But what happens is that t gets replaced by this x. So the answer here is f of x. The derivative of an integral simply means you're going to get this function. The only difference is what's up here is going to go replace t. So what I have here, I says derivatives and integrals are inverses of each other. They cancel each other out, just like multiplication and division. In example 1, the graph of f is the derivative of capital F of x. So f of x is considered to be something called the anti-derivative. So, what I mean by that is if you have a derivative, it came from something, correct? It came from a function. Like, if I have x cubed, and Tyler, I asked you the derivative of x cubed, you would tell me it's 3x squared. Everybody agree with that? Where did 3x squared come from? X cubed. How did we get it?
The integral.
We took the derivative, right? You take the 3 times the 1, you subtract 1, the 3 becomes the 2. That x cubed is the antiderivative of 3x squared. It's the original function. Is that kind of making sense to everybody?
So using integrals to find the to find the antiderivative
We will be, okay?
tomorrow.
No,
One.
next week.
Okay.
So you have to come back. Alrighty. Alright, so, trying to get this so you can see this. So, the fundamental theorem of calculus, part 2, says that you have differentiable equations here. You're taking the derivative of an integral. They're going to cancel each other out. You're taking the derivative of an antiderivative. What do you get? You're going to get this function. And what's going to be inside that function? G of x is going to be inside that function. Everybody okay with that so far? Now, I am taking the derivative, correct? The chain rule says, just wait a moment. You're not done. If you're taking the derivative, you have to attach something to this. I have to multiply by what? What's the chain rule say I gotta multiply by?
The derivative of g.
The derivative of g. Everybody doing okay? All right, so up here, when I had this,
We can't see it.
when I had f of x, Did I multiply by the derivative of x?
Derivative of x is 1.
1, so did I multiply by 1? Isn't f of x times 1 f of x?
Yeah.
Yeah. All right, so let's say we have something like this. What am I gonna get here? Well, I'm gonna have f of g of x times the derivative of g minus f of h of x times the derivative of h. And that why that subtraction is going to be there is going to be clearer next week. Okay? Can I flip it over? All right. So it says find the derivative of f. There's a little mark right there. So what I'm going to do is I'm going to write 3. I'm going to replace the t with x. And then I'm going to multiply by the derivative of x. Well, I'm going to multiply by what number? What's the derivative of x? 1. I just did, didn't I? Watch what happens here. I'm going to have the sign. I'm going to
I'm confused because it's hard to see. You tell me what you did for number 1 again?
all I did, wherever I see a t here, this is f of t. All I do to take the derivative of this is I'm replacing t with x. That's all I have to do. But if there's more to this function than x, I have to multiply by the derivative of that. So in this case, I'm replacing t with x cubed, but I have to multiply by what?
3x squared.
3x squared.
So 3x squared sine of x cubed?
That's the derivative, yeah, sine x cubed times 3x squared.
Okay. I think I get it.
Okay. So this one, I'm gonna write h. I'm gonna replace t with what? 4x. But then I have to multiply that by what? What's the derivative of 4x? 4. I'm done. Okay, let's look at this one. Wow, this is, I gotta figure out what's going on here. I have to get rid of this thing. All right. So, 5x. What's the derivative of x? 1. So I don't have to write anything. Minus
Is the answer 0?
5 times a negative x
But that's times a negative 1.
times a negative 1.
So the answer is 0, correct?
So I get 5x, I got negative, negative, negative. That makes it negative. And I get, what do you say the answer
0.
is? 0.
I think I get this one. I think I get this kind of stuff.
Okay, you want to try this one?
Okay.
Okay, I'm ready for you.
Would that be t 3x? No, would that be 3x squared
Okay,
minus 3x
okay.
times 3?
Oh, both of, would I multiply this by 3 also? Oh, the whole thing times 3.
Yeah.
Yeah, I got you. Minus what?
Minus 2x squared minus 2x.
And times 2 you said? You said at the beginning, right?
Yeah.
Yeah, it doesn't matter. Okay, so now I'm just gonna finish. Everybody with that? Understand what happened there? So you put 3x into t here, it's squared. You put 3x into t here, you have subtraction. But then you gotta multiply by the derivative of 3x, which is 3. Then it's minus, because that's the lower bound. Put 2x in for t, square it, and I forgot the 2x right here, made a mistake. But then you have to multiply by the derivative of 2. So this gives me 9x squared minus 3x times 3 minus 4x squared minus 2x times 2. I believe this is 27x squared minus 9x.
I did not simplify because I cannot see as well.
Is that better?
I'm just gonna put 27 squared, x squared minus 9x,
Yeah.
because I could simplify if I truly wanted to.
So do you see where I get a minus 8x squared?
I see how you could do that doing what you're doing.
Okay.
I see
And
how
you
that's
see
a
where I get a
possibility.
plus 4x.
I'm not seeing it, I'm not seeing it, but I understand that,
Okay.
that you could get that through these numbers.
Okay. And so my final answer is 19x squared minus 5x.
Hooter.
Yes.
It's your turn.